Hi everybody. Let's continue with the solve problems fusion wave in communication electronics. This one going to be a problem from chapter 6, Stillbauer electric and magnetic fields, and also have some problem related about plane waves and polarized plane waves. Problem 6.2b, a step function uniform plane wave is generated by suddenly impressing a constant electric field E equal to C at Z equal to 0 at time t equal to 0 and maintaining it thereafter. A perfectly conducting plane is placed normal to Z direction at Z equal to 600 meter straight total EX and eta HY versus Z and T equal to 1 microsecond and at T equal to 3 microsecond. As you plot the total EX and eta HY. Well, you know that the distance 12 d equal to v t, where v is the velocity of the wave. So that's in the air, 310 to the 6 meter per second. At t equal to 1 microsecond, that's the wave travels for 300 meter, and for t equal to 3 microseconds, the wave travels for 900 meter. Well, first of all, you need to see the relation, and you know that E over H equal to eta, or intrinsic impedance of the media. And now you also have a conducting plane. So when the wave starts traveling with velocity v at t equal to 1 microsecond, it's not really hit the conducting plane yet. So you have the plot look like this. And after the time passed by for 3 microseconds, the electric field will reflect from the conducting plane. But you know that there's no electric field at the conducting plane, so E plus E minus, or incident wave for EX minus, and EX plus, that's going to be reflected field. You know that at the conducting plane there's no electric field, so EX minus plus EX plus has to be equal to be 0. So that's the E minus equal to negative E X plus. When you add them up, you have a forward moving field, and this one you have the backward field. So you add them up, it's give you 0 along this point from 0 meter to 600 meter. For eta HY, it looks similar, except you know that your Hx minus going to equal to Hx plus. Sorry, I put supposed to put this one as x. So that's going to be the double of the magnitude of a field or let's give you sorry, this is supposed to be this one supposed to be double, okay, compared to a forward moving field. That's the problem 6.2b. So by summary, you know that for electric field at the conducting plane, you have no electric field. Let's check. Did I do? Okay. 6.3b asks you to sketch the locus of electric field for the following special cases of equation 6.31. This is the equation 6.31, identifying the type of polarization for each one. So you have E1, E2, and psi. So this one is about the polarization or wave polarization. Well, let's review equation 6.31. You have E with the component X and Y, and for Y you also have the phase different from the X component, which is you have the term E to J psi, and exponential negative K JKZ. This means the positive Z direction, right, of the wave. So the wave moved to the positive Z direction. Or your electric field, sorry, in the term of Z and T, actually equal the real part of the expression with the exponential of J omega T, or your EX component going to be E1 cosine omega T minus KZ, and for the EY component it's going to be your E2 cosine omega T minus KZ plus phi. That's going to be the phase different. And also the corresponding magnetic field H going to be equal to 1 over eta. You know the relation between E and H, right? E equal to eta H. And that's going to be your negative of unit vector X, E2, e to the J phi, plus the unit vector Y, E1, and then exponential J omega T, and exponential negative J KZ. This is in the time domain, and this is in the Z domain. Okay, let's get started. For E1 equal to 1, E2 equal to 2, and psi equal to 2. I just want to make it clear, so I just pick up this expression for both EX and EY. This is your EX and this is your EY. Since the psi is equal to 0, so you have EY equal to 2 cosine omega T minus KZ, because the amplitude is 2. Then you can see that this is the EX, right? Because E1 that's equal to 1. So EY equal to 2EX, that's become a linear equation. With the slope of what? 2. And you can also look for alpha. That's equal to arctan EY over EX, or in this case it's going to be arctan 2. For E1 equal to 1, E2 equal to 2, psi equal to pi. So your EY going to be your negative 2 cosine omega t minus kz. And you know this one is also EX, right? Because the E1 equal to 1. And you have the negative slope, or negative 2. Also be able to look for alpha. So this also become linear. So very straightforward for this problem. For E1 equal to 1, E2 equal to 1, and pi equal to pi over 2. Consider EY cosine omega t minus kz, or cosine A plus B equal to cosine A cosine B minus the sine A sine B, right? Cosine pi over 2 equal to 0, so this term drop. You have only a negative sine omega t minus kz. Now you can see that EX squared plus EY squared, that's equal to 1. This is the circle equation, right? And with the radius 1, you have the coefficient of E and EX squared and coefficient of EY squared, they are equal, so that's give you a circular. That's the basic math. And since the sine equal to pi over 2, and this going to rotate in the direction of clockwise, as shown by the arrow. For E1 equal to 1, E2 equal to 2, but your sine equal to pi over 2. Your EY going to be your negative 2 sine omega t minus kz. And you can see that for cosine square omega t minus kc plus 4 psi square omega t minus kc that's going to equal to 4, because cosine square plus sine square equal to 1, right? And cosine square actually is EX squared, and sine square actually EY squared. So this gives you elliptics. And for this one, I just work out to draw the plot. For EX equal to 0, you know EY equal to plus and minus 2. And for EY equal to 0, EX equal to plus and minus 1. So you have the elliptics look like this. Sorry. Last one. E1 equal to 1, E2 equal to 1, psi equal to pi over 4. So you expand this term. We end up with EY equal to 1 over square root 2, because the cosine pi over 4 equal to 1 over square root 4, and that's also equal to sine pi over 4. And then cosine omega t minus kz actually EX, so that's why I have EX right here. And your sine you can write in the term of EX become, or in the term of cosine, that's equal to a square root of 1 minus cosine square, right? Where cosine square actually is EX squared. You rearrange the term, you end up with 2EY squared minus square root EXEY plus 2EX squared equal to 1. This is become a tilted elliptics, as shown. I also do the summarized. That's supposed to be okay. I summarize here. We start with the electric field equation. And then you have EX and you have EY, and also the corresponding magnetic field. Let's consider linear phase polarization with the condition if the two components of the fields are in phase or psi equal to 0, you will get a linear polarization where your alpha equal to R10 or EY over EX, or R10 or E2 or over E1. That's the condition for linear polarization, or sometimes they call plane polarization. Sorry. Circular polarization. E1 equal to E2 and pi equal to plus or minus pi over 2. So your alpha equal to R10 or EY over EX, and you end up with minus and plus omega t minus kz. This one I just want to point that if your psi equal to plus pi over 2, this leads to alpha to be negative omega t minus kz. So that means this one you rotate in CW or clockwise, because you know that the anchor become negative, right? If you rotate the wave in clockwise, sorry. And for psi equal to negative pi over 2 leads to alpha equal to positive. So this means we're going to rotate in the CCW or counterclockwise. For elliptic polarization, E1 not equal to E2, or if E1 equal to E2, but psi other than 0 or plus and minus pi over 2, cannot be this one. Okay, so that's the about wave polarization, to analyze, you know, what type of polarization is. Problem 6.3d. Show that any arbitrary elliptically polarized wave may be broken up into two oppositely rotating circularly polarized components instead of two plane polarized components. Okay, so you're talking about elliptical polarized. You can write in the term of two plane polarized. This one a little bit tricky. You need to think a little bit. Okay, we start from field equation. And we know that circular polarization form when your psi equal to plus and minus pi over 2, right? So exponential j pi over 2 actually equal to j. So you have a minus or plus j E0. Okay. So from 1, you just break this one apart. So I break half and half of E1, so I have a unit vector x E1 over 2 plus unit vector x E1 over 2. Let's give you back to E1. Same as for y. Here. And then I want to break up into oppositely rotating circular polarized. You do this by following all steps below. Okay, take a look carefully. So what I did is that I add negative jy because I need the unit vector y, right? So I add unit vector y, negative j because you also need j, and you have our E1. So you have our negative j, the same coefficient for all the magnitude of the field, the x component, E1 over 2, and then negative j. So you have to plus jy, unit vector y, E1 over 2. Okay, same as for this part. I used the red ink to show you this is what I add. So I have a negative j. I want the coefficient to be E2 over 2. So I have E2 over 2 here, and when you add negative j unit vector x E2 over 2 exponential j psi, you need to plus j unit vector x E2 over 2 exponential j psi. And I sorry, I put the let's take a look at the coefficient E1 over 2. So this is your E1 over 2, and this is the common term E1 over 2. So I have a unit vector x minus j unit vector y, which is come from this term. And also this one. Okay. For this term, you have sorry, I take this term first. The common term is E2 over 2. Okay. You take her. Hold on a second. I don't want you to confuse. Let's see the common term first. E2 over 2, and then E to j psi, because you want this one in the form of a circular polarization, so you need j. So that's why you add j to y, so you have to divide it by j. Okay. When you multiply back in the bracket, it's back to be only your unit vector y, right? And then multiply by E2 exponential or j phi for this term. And also for the x component, unit vector x, and for this term is turn out to be this term. You take a negative psi out, so you have only x unit vector x minus j unit vector y and exponential negative jkz. Okay, so that's why I say a little bit tricky. And you take a look at this one here. You put this term together, so you have E1 over 2, right? And this is the coefficient is the E2 over 2j, or simply a negative E2j over 2. So that's why I have this term. Alright, same as these terms. You add them together and you end up with E1 over 2, and then minus hold on a second, got to be careful. Sorry, okay, this is plus and plus. Actually, it's right here. Did I do something wrong? Well, you check the side back. This is the x plus jy, x plus jy, so this term. and that's supposed to be positive, right? And for x minus jy, which is this term, that's supposed to be a negative sign. Okay, correct. Sorry. And that's this one's supposed to be your positive sign. Sorry for my mistake. So for this term with positive, this is going to be what? A clockwise circular repolarized ray. But for this one, it's negative j, or your pi equal to what? Negative pi over 2. So this one going to be a counterclockwise circular repolarized. Okay, so that's the problem 6.3d. They want you to show that any arbitrary elliptically polarized net can be broken up into opposite rotating circular polarized components. Let's go to page number 76. Okay. Problem 6.4b. Plot a curve showing our attenuation constant in seawater from 10 to the 4th to 10 to the 9th hertz, assuming that the constant given do not vary over this range. Comment on the implications of result to the problem of communicating by radio waves through seawater. Simply want you to plot your alpha or attenuation constant. Well, from the textbook, table 6.4b, for seawater, your sigma equal to 4 and epsilon prime equal to 81 epsilon 0. So this is the relative permittivity of the seawater. And you know your epsilon 0 equal to 8.85 10 to negative 12 in the unit of farad per meter. This is for free space. We assume this to be independent of frequency. For if your frequency is equal or less than 10 to the 7th hertz, you can consider this as a good conductor, so that you can use the approximate equation. Your alpha simply is about square root of a pi f mu or sigma. That's equation 6.412. When epsilon double prime over epsilon prime is about sigma over omega epsilon prime, or much greater than 1. At higher frequency, from equation 6.45, you have alpha equal to this expression. Okay, just use the spreadsheet or Excel, to plot this plot. This is what I got. This is your attenuation constant, and this is the frequency. So 10 to the 4th, 10 to the 9th. So you plot look like this for the attenuation constant, okay, with different frequencies. Last problem from this series, 6.4c. A horn antenna excited at 1 gigahertz is buried in the dry earth. How thick could the earth covering be if half the power is to reach the surface? Okay, so you have talking about a plane wave. You have incident wave you have a reflected wave, and some of them will transmit to the surface of the dry earth. Neglect reflections at the surface in your first calculation, and then estimate additional fraction lost by the reflection. Okay, so you talk about incident, you talk about reflection, and you're also talking about transmission. Where your power ratio from page 285 of the textbook is equal to exponential negative 2 alpha z, where alpha is the attenuation constant and z is the depth. So to get a 1.5 power, simply have a 0.5 equal to exponential negative 2 alpha z. We apply ln or ln to both sides of the equation. You end up with z equal to ln 0.5 divided by negative 2 alpha. So you need to look for your alpha. And this is your equation from the book. Now let's consider for the dry earth, your sigma equal to 10 to negative 3 cement per meter, and your epsilon prime over epsilon 0 is equal to 7, or actually your epsilon r equal to 7 relative permittivity. So you have your epsilon for the dry earth equal to sorry, R7 multiplied by epsilon 0. Let's give you a 6.2 10 to negative 11 farad per meter. For conductor, epsilon double prime over epsilon prime, because you need also this term, right? Equal to sigma over omega epsilon prime. And your sigma for dry earth is 10 to the negative 3 Siemens per meter. Omega equal to pi f. And the frequency given is 10 gigahertz. That's 10 to the 9th hertz. And your epsilon prime 6/2 10 to negative 11 farad per meter. Just plug in the number, you end up with your alpha, or attenuation constant equal to 0.07 That's in a meter, right? So your z equal to 4.88 meter. That means your power will drop into 50% when the wave transmit into the meter for 4.88 meter. Now they also ask you neglect reflections at the surface in your first calculation, and then estimate additional fraction lost by the reflection. They ask you to calculate the fraction lost by the reflection. In this case, you need to look for the reflection coefficient, which is rho equal to eta 2 minus eta 1 divided by eta 1, eta 2 plus eta 1. Sorry, my mistake here. It's supposed to be positive. For the air, your eta equal to 377 ohms, or square root mu 0 over epsilon 0, right? And for dry earth, eta 1, that's going to be a 377 divided by square root epsilon r. Sorry, this is supposed to be epsilon r. And you end up with your reflection coefficient to be 0.45. Fraction of power transmitted at the surface then to be 1 minus the magnitude of your reflection coefficient square, and that's give you 0.8. That's the transmitted wave. To get 1.5 of antenna power, you need so you put the ratio of 0.5, this is the 1.5 power, and divided by at the surface you have a transmitted wave to be the ratio that's to be 0.8, and you end up with the ratio 0.625 of antenna power just inside the surface, because there as you also were to but negative deflections at the surface. Then sorry, the power ratio instead of 0.5 now it's turned out to be 0.625 divided by 2 alpha attenuation constant. That's give you a 3.3 meter. Okay, so that's about our antenna. Okay, here that's all for this series, and I'll see you in the next series.